Hello, everybody. Today I'll be talking about PDE-constrained optimization with PETSc TAO. We'll start with some theory overview that might be familiar to some of you, and then I'll go into the software and the hands-on example. So we'll start with the very basics. Optimization at its core is just about finding some set of inputs that minimize or potentially maximize a function of interest. As a simplification, you might remember from calculus, it's just, it's minimized from where the gradient is equal to 0. It's broadly broken up into two categories, gradient-free and gradient-based methods. Gradient-free methods just search through the space of the optimization variables without evaluating the derivatives. And the gradient-based method uses the derivative to assist that search. And in what we do in PETSc TAO, we go with the gradient-based method, and that's going to be our focus for this talk as well. Most importantly, though, why do we care about optimization? We've spent most of the day talking about forward problems where we have some physical system, we feed it inputs into it and compute the outputs. But a lot of scientific questions appear as inverse problems where we have some output of a physical system that we want to manipulate, and we want to find the inputs that achieve the results we want. My background is in aerospace engineering, so I use a lot of pictures from there, even though it's not in the DOE sphere of interest. But just to give you some examples, this is a shape optimization problem. We have our structural and fluid dynamic simulations and feeding in geometry and trying to minimize things like drag under constant lift and problems like that. So these are the types of problems we want to solve, leveraging what we already know about the forward problems so that we can do control, design, prediction, decision. So to that end, I'll go through PDE-constrained optimization, how those problems are formulated, introduce the software package, and discuss sensitivity analysis, essentially computing the gradients for these methods. And then we'll go through the hands-on example. So PDE-constrained optimization is a special optimization problem where we have the objective function, but we also have a partial differential equation imposes a constraint to the optimization problem. In this case, an equality constraint, more specifically. And the partial differential equation, we tend to express it as just state equations. So this is a set of equations we have to solve to find out the state of the PDE that corresponds to the inputs or the parameters P. Here are the optimization variables. U are the states for the PDE, and this is what's called the full space formulation because the optimization problem itself includes both the optimization variables and the PDE states. In the traditional gradient-based approach, we construct a Lagrangian that includes both the objective function and the constraint, which is the PDE in this case. We differentiate it with respect to all of the inputs, and we're trying to find the point that gets these to 0. That's our minimum. And the most natural thing to do in this situation, this is a root finding problem. Let's apply Nun's method. And we end up with this Shelifin algorithm where we essentially solve this really nasty looking system. And when I say solve, I am being very loose, not rigorous. There's a lot of ways to solve this type of problem, not necessarily a matrix inversion, but approximate solutions, conjugate gradient methods, quasi-Newton methods. If you do want to do a monolithic solve, you can. But ultimately, this is a very large saddle point problem because of that 0 block in the lower right. a bit of a headache to solve. It has the advantage that we're not doing full PDE solutions. It's all embedded in there. But this is one approach, and there's lots of people doing research in this sphere, but the tight coupling between the PDE solution and the optimization makes it difficult for people like us to write general use optimization libraries that you can plug and play your problem into. To address that, we go to what's known as a reduced space formulation. This is where we use the implicit function theorem to eliminate the constraint. The state variables just become a function of the parameters, and now it's decoupled. But of course, the downside of this is every time we want to evaluate the objective function, we have to solve the PDE fully to get the corresponding states. However, this is the way we're going with. As I mentioned, the decoupling is necessary in order for us to be able to write general purpose optimization libraries. So as part of PETSc, the Toolkit for Advanced Optimization is the component of PETSc that does optimization. And this is sort of like a very loose overview of how the hierarchy works. PETSc has a lot of different packages in it, the vector matrix, linear algebra stuff, the Krylov solvers, and the preconditioners, nonlinear solvers, and TS is a time-stepping package. TAO is meant to go around all of these and use all these components. Essentially, what you see inside, that's the forward problem. And TAO is using that information to solve the inverse problem. And it could, in principle, exist as a separate package, and it used to be. But we distribute with PETSc, and you can download it here. There's other similar packages. The Rapid Optimization Library is a similar package that is based on Trillnos infrastructure. And then there's also HiOp, which is essentially a parallel version of interior point method. The main things is TAO is parallel. So all of the optimization data structures parallelize automatically with PETSc data structures. We're doing gradient-based methods. Currently, we're only supporting bound constraints, but work on nonlinear constraints is ongoing at the moment. So basic TAO main program looks like this. PETSc initialization, we create one vector that represents the optimization variables. We create the TAO solver, set the type, set the initial vector, and then pass a function pointer into TAO that represents the function and gradient evaluation. That function pointer is right there. So this is where somebody who has a PDE solver who wants to use TAO comes in and provides this function, and the TAO algorithms just do callbacks to get the necessary information. And that looks something like this. This is where TAO provides the optimization variables and the gradient vector and the objective function that needs to be computed. So this is where users do their work. And we'll see an implementation of this later in the talk as well. So as I said, the steps are pretty straightforward for this. The important thing is this sensitivity analysis bit. As I mentioned, TAO does gradient-based optimization. We need those sensitivities computed. The advantage of gradient-free methods is that we can converge to local minimums faster than gradient-free methods, fewer function evaluations, which means fewer PDE solutions. This is really important for PDE-constrained optimization. When you think about the relative computational costs, the vast majority of it is in the PDE solution. The optimization problem itself is relatively cheap. So we want to evaluate the function as little as possible. And in this talk, I'll talk about two methods of computing this gradient, the finite difference approximation and the discrete adjoint method. And we'll compare how those work in computational cost and so on. So the finite difference method, very straightforward. Perturb the inputs one by one, get the outputs, central difference, forward difference, whatever you want to use. Very easy to implement. You only need the PDE solution and the function evaluation. Scales very poorly with the number of optimization variables, and there's the step-side dilemma issue. The adjoint method is what you would want to do to get around these problems. And to describe what that is, I'll refer back to the optimality conditions that I put up before. The adjoint method is like essentially solving equations 3 and 2 fully and plugging into equation 1. So we start by solving the PDE itself for a given set of optimization variables. And then that gives us the PDE states at that point. We linearize this adjoint problem. That's equation number 2. At that point and solve for the lambda terms. Those are the Lagrange multipliers. And then we go back and plug into equation number 1. That gets us the gradient. So this method is independent of the number of optimization variables. So it doesn't matter how many, it doesn't matter what the size of P is, you're only doing one adjoint solution to get the gradient, and the size of that adjoint problem doesn't change. The flip side of it is it requires the adjoint operators for the PDE Jacobian. Some PDE solvers already have this, some don't. In some problems it's possible to shortcut it. We'll see that shortly as well. I also want to mention that the time stepping package in PETSc provides checkpointing. If your problem is time dependent, then your adjoint solution has to be backwards in time, and the infrastructure to do that is available as long as you have the transpose operator for the for each time step. Then we can compute the adjoint for these problems as well. So the hands-on example for all of this, we'll do a simple boundary control problem. This objective function that you're seeing is a very standard inverse problem. We have some target solution on the right edge of the boundary that we want to recover, and we are manipulating the bottom left and top Dirichlet boundaries for the problem to recover that solution. The governing equations here, I put them up. These are not equality constraints in the problem. This is just the governing equation. So this stuff is what we solve to find the states in a given P. So in this particular example, I've set the target solution to a simple parabola. We can play around with that this evening, see what happens. And the underlying PDE solution, the objective function, the gradient calculation is all done through AMREX here. Thanks to Don for his help setting a lot of that up. And we're taking advantage of the fact that the governing equations here are self-adjoint. So the PDE Jacobian, although AMREX is a multigrid solver, it doesn't really have this in pure matrix form. But if the PDE Jacobian was a matrix, it would be symmetric. In this case, the operator is self-adjoint, so we can simply use the forward solution to also do the adjoint solution. And we're going to be play around with some command line options, see what happens with this. And just to give you guys an idea before I switch over, this is, we're starting at a flat solution of 1, and we're recovering this at the end. That missing line is just a visualization artifact. So I'm going to switch over to oh yeah, absolutely. Yep. Better? Okay, so if you run your rsig command again, Over here, you'll get the latest version of this. And it should compile. Actually, I shouldn't be doing this here. So while that's coming along, I just want to share something here. We have a lot of different command line options available, some TAO settings that are relevant to us, some of the problem parameters. By default, this is solving a 128 by 128 problem. It's pretty small. And I'll start with serial, and then we'll go from there. So executable, first of all, we have to provide the inputs file for MREX. You saw that happen in some of the earlier hands-on examples. Then we'll enable the TAO monitor. This will give us iteration information. And we're only going to want to converge this down to, this is the function tolerance. So it's going to be monitoring the function value. In this case, our function value is a representation of error. So that's, this is a reasonable thing to do. In a lot of design problems, you would want to converge based on the gradient norm tolerance, but we can take a look at that too. And finally, changing the line search type to Armijo. This is a backtracking line search, so it's going to be pretty straightforward. And when we run this, we can see it's taken 22 iterations. This is running with a quasi-Newton method. And you can see that it terminated as soon as it cleared the function value we're looking for. If we run this with the plot option, it's a little bit slower, but it generates the plot files we want, and we can take those off, go into ParaView, visualize them. You guys have done some of this with the MRX sessions earlier today, but ultimately this is what we get out of that. So the first thing I want to do with this is go to a 64 by 64 problem, because 120 by 120 is a bit much for the finite difference method. We'll be sitting here a lot. And then enable the finite difference method, and you can immediately see that it's just slow. Because this is ultimately doing about 192 function evaluations every time it needs to compute a gradient. It still converges, and actually about the same number of iterations as well, 23. One of the things to note is the so this, where it says residual, this is the gradient norm, and they're slightly different. The adjoint method is the accurate one. There's some finite difference errors creeping in here. Yeah. So we can actually get this. Yeah, so with the finite difference method, you're essentially doing a small perturbation to each parameter, right? Taking the difference. There's truncation errors involved, and because of that, the gradient norm is very slightly different between the adjoint method and the finite difference method. So that error doesn't just, the finite difference method doesn't just slow the problem down in terms of computational cost, but also slows the algorithmic convergence. So it actually takes potentially a few more iterations because of the errors in the gradient. And so I guess the point of that exercise is motivating the use of the adjoint method. That if you want to do PDE-constrained optimization, finite difference method is great for prototyping. It's great for small problems, but the residual is the norm of the gradient, because in optimization problems we want to find the point where the gradient of the objective function is essentially 0, and we try to get close to 0, and so that's the measure essentially, just taking the norm.
Sorry, I think a few of us are having compilation problems.
Yeah.
I was just wondering if what's in your soft file to see if we've...
I don't have anything at all in my soft file.
Okay, so do you know what G++ compiler version you're using? We're getting undefined references to C++ standard library functions.
It's in the main file.
Yeah.
There's a reference with permission denied.
Oh.
There's a path in the main file with permission that gives...
There's a here.
You might want to rsync again. Or just copy the makefile again.
Yeah. You might want to just do an rsync again to get the latest version.
Yeah, do an rsync as Alp is requesting, and if you continue to have problems, either look for now, since we're doing a live hands-on lesson, maybe with someone that's nearby you, and we can try to actually get you to work through parts that you weren't able to work through later this PM in the evening session.
But yeah, this is what my makefile looks like in the latest version, and I don't think this has changed since early morning. But if you've done an rsync at the very beginning of the day, you haven't updated since then you might have a broken version. Did that work? No?
I think it's a new GCC. I'll change it.
Okay. Yeah?
I think when you're passing and the file already exists, you need to replace the dot by the name of the folder.
So if you're doing off the home folder,
Yes.
if you're calling rsync off the home folder, and there's a dot there, then it'll just copy that whole hands-on thing into the.
I think it only has that behavior the first time when the folder doesn't exist yet. But here, if I do the rsync dot, it is going to copy all the folders inside.
Okay, so before you do the rsync, if you go back out to your home directory and do the rsync, rsync will essentially compare what's there with what's at the source. Am I correct about that? And only update the difference.
Make sure you don't leave.
No, it's working on
Yeah.
Steve.
Yeah, it's working as well.
Yeah, it still doesn't update.
Alp, why don't you continue with your parts
Okay.
that are working for you? I'll see if I can.
Okay.
Tab completed. So I can the backslash here equals in terms of this is slash asterisk so that it ends up.
So because the finite difference run was taking quite a lot of time, I went to run this in parallel, which, by the way, this is the exact same code that was running in sequential because of the nature of the underlying libraries. Everything's scaling up easily. So now if we go to then this should actually, yeah, much better. So because the PDE solutions are now in parallel, it's still slower, but at least we're going to reasonably get this to a solution. Yep.
Yeah, I think there was a GCC that we had to our soft files before.
Okay.
I removed that and I enabled the file out.
Okay. Okay. So yeah, I don't have anything in my soft file. It's just what, whatever you have loaded from previous sessions, getting rid of that clearing, those will get this running. So this is run with the finite difference flag, and we're still looking for the function value to drop below 10⁻⁶, and it's not, and it's terminating early. So we can do TAO converge reason and figure out why that is. It's going to run again, will tell us what it failed on. But this happens because of the finite difference errors, particularly when the gradient gets small. This is error dominated, and we're essentially start getting garbage search directions that impact the, yeah, you can see line search failure. So it's just getting bad search directions. So this is a limitation of the finite difference method. Slower, small gradients are error dominated, and it's good for prototyping, but with PDE-constrained problems, you really would want to implement the adjoint method. So I wanted to take a quick look at the source code. So this right here is the actual problem file we used to set up. We have the package initializations here. So this is one thing I want to draw your attention to. We create the PETSc vector here. And the sizing of this PETSc vector essentially comes from this MyTest, which is the Poisson problem implemented with AMRX. And we're getting the number of boundary values that we're controlling and generating the vector that way. And what this essentially means is that when we go into this this function where we evaluate the objective function, essentially we get the PETSc, we get the boundary information from TAO optimization algorithm, and we set it into the MRX problem. And in this process, there is no communication here because we've sized up the vectors properly ahead of time. The vector on the TAO side has the same number of local elements as the information on the MRX side. So we propagate this stuff without communication, and it just scales up easily. So the advantage to using libraries like this is, this was being discussed a little bit in the panel, is it softens the blow of dealing with parallelization. My background is in engineering, not computer science, not even applied math. Coming into this, these types of tools make it considerably easier. So yeah, we've done the finite difference, the same 64. So with the finite difference method, this is measured in microseconds here. I'm just using the standard C chrono package to get this information. And when we run the same problem with the adjoint method, it's a fraction of the time. And later on in the evening, we can play around with different problem sizing to see how this scales, because we can go to 120, for, essentially more than double the size of the problem, and there isn't much of a significant difference. This is the advantage of the adjoint method, that we can do this independently of the size of the problem. And I think maybe the last thing I want to take a look at is verifying that the finite difference problem is actually generating the same results. So I have the Cooley home folder mounted here. We can go to it just needs to load it. Oh, okay. Because I need to turn on plotting. Was everyone able to get the problem running? You guys? Running? Okay. Okay. That's good enough for now. Yeah. So these are all the plot files that come from computing the gradient. Yeah, that's a lot of plot files. There we go. Really? Parity problems. Well, I guess we're not doing visualization right now. We can take a look at it in the evening, but the finite difference method essentially generates the same results here. One of the other things I want to point out here is with the finite difference method. So we have two functions here. One is form function. This is a callback for tau that only computes the objective function, not the gradient. There's another one that computes both the objective function and the gradient at the same time. So we have this problem running in two different modes. One is when we're doing the adjoint method, we use this interface to set the function that computes both the objective and the gradient at the same time. When we're doing the finite difference gradient, the first function sets only the objective callback. There is a provided function by tau called tau default compute gradient that gets set in as the gradient routine. This one does finite differencing for you. So if you want to come in with your PDE solver, you want to prototype the problem, you don't want to worry about the gradient, all you need to do is a simple forward solution and the objective function computation. We'll take care of the gradient for you. It just won't be fast and won't be very highly accurate. But that's okay for prototyping. So I'm going to go back and wrap up some things here. Well. So we talked about computational cost of the finite difference gradient versus the adjoint method. we did see that adjoint method is mostly independent of the size of the problem. And we'll solve this with different algorithms in the evening session. But the main takeaways that I want to come with is if you have a PDE solution and you want to do some kind of inverse problem, don't try to code up your own optimization algorithm. And the most common ones out there, like in Python, for instance, are all serial codes. We have the interfaces that support reduced space PDE-constrained optimization formulations, and this optimization library runs in parallel. So if you have a parallel PDE solver, you can make this work without using global arrays, without doing a lot of extra communication. There are automatic tools in TAO for computing gradients and Hessians, though we talked about their limitations. Big thing is PETSc data structures are easy to couple with most of the PDE solvers. We can get C array information for all the local data. It's pretty straightforward. The adjoint method is really good. We talked about that. And one more important point is that all of the data structures we use in optimization algorithms are all duplicated from this initial vector provided to TAO by the user. What this means is that you can set up your own parallel distribution, whether it's on the GPU or the CPU, and the entire algorithm will just duplicate off of that. So the algorithm essentially fits the PDE solver. And there aren't very many tools out there that have this, and I think it's very valuable. So I'd like to put up some links here and acknowledge Don again for his help. And if you guys have any questions, I'll spend the last 2 minutes with that.
So if you want to use that joint method in TAO, what are the things that your PDE code has to provide?
So here, let me go back to the code real quick. So what we're doing here, at least in this problem, is in the function that computes the objective and the gradient, we have the straight objective call, but then there's a solve adjoint system problem. And essentially all this does is it sets the right-hand side for the forward solution to the partial derivative of the objective function. Essentially it's this system right here. It's this system right here that's highlighted. It's a little bit small. I want to go to the slides and show you this. Okay. It's the one at the bottom. Sorry, the one at the middle. This one right here. So that's the transpose operator for your PDE Jacobian. The right-hand side is the partial derivative of the objective function with respect to the PDE states. In this problem, because the governing equations are self-adjoint, we can use the forward solution as the adjoint solution. We change the right-hand side in the setup, and then we solve the forward problem again with the new right-hand side, and then we plug that into the equations we discussed to compute the gradient. For a problem that is not self-adjoint, you need the adjoint operator. In many cases, people do automatic differentiation for this. There's some tools that will actually do this for you, though most of them require source code cleanup. But in many ways, this also comes down to problem formulation. If you can structure some kind of a self-adjoint problem, you're saving yourself a whole lot of extra work.